Section 32.4, Entropy. For a system that contains uppercase N distinguishable particles which occupy lowercase n energy levels, assuming the Boltzmann distribution, the total number of microstates is given by this equation. W, the number of microstates, is equal to uppercase N factorial over A1 factorial, A2 factorial, A3 factorial, etc. Again, the uppercase N is the number of particles, and A1, A2, A3 are the number of particles that occupy the first, second, and third energy levels. So this A sub I over N is also the probability of finding a particle that occupies the ith energy level. And AI over N is equal to e to the power of negative beta epsilon I divided by the sum of e to the power of negative beta epsilon I. Beta is the reciprocal of kBt. Boltzmann proposed an entropy equation. Entropy is equal to the Boltzmann constant times the natural logarithm of W, where W is the total number of microstates accessible to the n-particle system. So we can do the following derivations. Entropy is equal to K sub B, the Boltzmann constant, times the logarithm of the number of microstates. And over here, this is the expression of the number of microstates when A1 particles occupy the first energy level, A2 particles occupy the second energy level, etc., etc. And then we can just separate these two terms, and then we use Stirling's approximation. The Stirling's approximation is this: the natural logarithm of x factorial is approximately x times ln x minus x. So I'm using this Stirling approximation here and also here. And now this n and the sum of AI cancel, because the sum of A1, A2, A3 all the way up to A sub n is equal to the total number of particles. So again, this part, this is negative uppercase N, and over here this is actually positive uppercase N, because it's negative, negative uppercase N. So now we have only two terms. Now we will rewrite this uppercase N as the sum of A sub I. And this is because we would like to combine these two terms. So now we combine these two terms, and then we get this expression here. The reason I put a negative sign here is because supposedly it's n over AI, but right here I'm writing AI over n. Therefore, I need to add the negative sign in front of this sum, or in front of the Boltzmann constant. The reason I put A sub I on top is because A sub I over n is the probability of finding a particle occupying the ith energy level. So AI over n is written as P sub I, and P sub I is the probability of finding a particle occupying the ith energy level. And again, this A sub I can be written as the total number of particles, n, times the probability, P sub I. And now we have this equation. We can tell that this n and this n cancel. So this equation can be used to calculate the entropy of a very large system. And if you delete this K sub B, if you divide this final expression by the Boltzmann constant, you will get the informational entropy in information theory. So there's also a concept similar to the thermodynamic entropy in information theory. And their definition of entropy is just negative n times the sum of pi times the logarithm of pi. Again, P sub I is the probability of a particle occupying the ith energy level. the sum of pi should be 1, and pi is the e to the power of negative beta epsilon I over the sum of e to the power of negative beta epsilon I. So this is the so-called Boltzmann distribution. The denominator is simply the partition function Q. And the partition function Q for atoms or molecules can be written as the product of the translational partition function, rotational partition function, vibrational partition function, and electronic partition function. For atoms, we do not have the rotational or vibrational modes. Therefore, for atoms, the partition function of rotations and vibrations are equal to 1. This probability depends on the energy spacings rather than the absolute energies of the particles. So we can simplify the expressions of the vibrational partition function and the electronic partition function by having the 0K internal energy as the zero reference. What does this mean? That means we just assume the 0 point vibration energy is 0 here. So we arbitrarily choose this half h nu for a vibration mode to be the zero reference. And also we say this Q of the electrons is 1 by setting the 0K electronic energy to 0. We use the 0K electronic energy as the zero reference for the electronic partition function. We set the 0 point vibration energy to 0 as a reference for calculating the vibrational partition function. So in short, we neglect the 0 point vibration energy and the 0K electronic energy. So in this regard, the third law of thermodynamics is arguable in declaring that the entropy of a perfect oxygen crystal to be 0 for many reasons. First, both potential and kinetic energies are relative quantities. So when we are talking about potential energy, it depends on the relative positions of the particles. And even for kinetic energies of the particles, you have to look at the relative motions of those particles. So both potential energy and kinetic energies are just relative quantities. You can't just calculate the 0K electronic energy and say, well, it is the absolute energy of the particle. It's not, because you can somehow imagine there's a strong repulsion between the two protons in the nucleus of the helium atom, right? We didn't include that in our equation. So again, the 0 point vibration energy plus the 0K electronic energy is again relative to separate nuclei and electrons. Second reason, the third law of thermodynamics is arguable, is that the nuclei and electrons in the oxygen crystals are constantly changing their momentum and positions, even at 0K. So you can't just declare that there's zero disorder, or it's completely ordered. So there are uncertainty about the momentum and positions of the electrons for sure, even at 0K. There's a third reason why the third law is arguable. The grounded electronic state of oxygen, molecular oxygen, is a triplet. So really, even at 0K, you should think about the three different microstates regarding the spin of oxygen. All right, it can be alpha, alpha, it can be beta, beta, it can be alpha 1, beta 2 plus alpha 2, beta 1. So that being said, the third law of thermodynamics provides us a convenient way to calculate the entropy of a gas. So now let's try to calculate the absolute value of the entropy of a gas. The reason I emphasize gas is because it's easier to compute the rotational entropy for a gas. If you have a solid or liquid, you may assume the translational entropy is 0 in a solid or close to 0 in a liquid. But somehow, if you need to calculate the rotational entropy of the molecules in a liquid, it's very difficult because all molecules are, I think, undergoing hindered rotation. So even for a, let's say, water liquid, each molecule, water molecule forms multiple hydrogen bonds in liquid water, but still it's possible for the water molecules to rotate. And also it's hard to compute the vibrational entropy as well due to the interaction between neighboring water molecules. So let's just focus on the gas. The partition function Q is equal to the product of the translational, rotational, vibrational, and electronic partition functions. And this is the formula for the translational partition function, 2 pi m kBt to the power of 3/2 times the volume of the container divided by the Planck constant to the power of 3. If you have a real gas, it's probably more accurate to replace the volume of the container with the available space. It's going to be just V minus mv here, all right, if you have a real gas. And also, you need to take the attraction and repulsion between the real gas particles into account when we try to solve the particle in the box problem. So that gets too complicated, so I'm actually assuming it's an ideal gas right here. Now this is the partition function for the rotation of a linear molecule. It's kBt over sigma hCb. Sigma is the symmetry number or the symmetry factor. For example, sigma is 1 for HCl, but sigma is 2 for H2, Cl2, O2, or N2. You can look up the value of the symmetry numbers in chapter 31. This is for nonlinear molecules. They can rotate about the x, y, and z axis, and therefore it's actually the product of 3 terms. Each term corresponds to one rotation. And then over here, this is the square root of pi over sigma. Again, sigma is the symmetry number. Over here, these 2 equations are the vibrational partition functions for linear molecules and for nonlinear molecules. They are very similar to each other. The only difference is this. If you have a linear molecule, there are 3 translational modes and 2 rotational modes. Therefore, there are 3 and minus 5 vibrational modes. For nonlinear molecules, you have 3 translational modes and 3 rotational modes. So there are 3 and minus 6 vibrational modes. So that's the only difference. 3 and minus 5 versus 3 and minus 6. Over here, again, in these 2 equations, we neglect the 0-point vibration energy. If we include the 0-point vibration energy, we need to replace this 1 with e to the power of negative 1/2 h nu times beta. So, but again, the 0-point vibration energy does not depend on temperature, and that's why we can safely neglect that constant when we calculate the entropy. So now let's look at the electronic partition function. I'm going to just assume it's 1. Even for the oxygen molecule, we're going to just assume it's 1. I know at 0K, the ground electronic state of a oxygen molecule is a triplet. So supposedly it's 3, but then we'll have to kind of just write the third law of thermodynamics, right? So again, I mean, it's just because of the three reasons I stated before. It's okay to just arbitrarily say, well, the entropy of a oxygen crystal, a perfect oxygen crystal, at 0K is 0. Now let's look at the equation for entropy again. This is the entropy for the equation for entropy, and P sub I is just e to the power of negative beta epsilon I over Q. So we have this equation. We just replace every P sub I with this expression, and then from here to here is just algebraic derivation. I think over here you have a division here, so it becomes subtraction here. It's negative beta epsilon minus ln Q. We see a negative sign here, negative sign here, negative sign here, so we kind of simplify this. Now we have just a beta epsilon I plus ln Q in the parentheses. All right, and then we separate these two terms. We get these two terms, and over here, this part is simply Q. So Q and Q cancel. Okay, Q and Q cancel. So the second term is simply ln Q. Now let's look at the first term. I'm going to prove that the first term is the product of T and the first derivative of ln Q with respect to T. So I'm gonna go backward. So temperature times the first derivative of ln Q is this. I multiplied this T by Kb and this T by Kb. That's okay. All right, that's this is fine. And then d ln Q is dq over Q, because the first derivative of ln Q is 1 over Q, so that's why. And then kbt is just 1 over beta, so I replace this with 1 over beta and this with 1 over beta. And the first derivative of 1 over beta is negative 1 over beta squared times d beta. So that's why I rewrite this to be just d beta times negative 1 over beta squared. And then we do some simplification. You have this formula here. And then you can see dq over d beta. What's dq over d beta? dq over this is q. So dq over d beta is the sum of negative epsilon I times e to the power of negative beta epsilon I. So therefore, you get another negative sign when you take the derivative of q with respect to beta. And that negative sign and this negative sign cancel. So this is our final expression for t times d ln q over dt. And this part is the same as this part. All right, so this part is simply t times d ln q over dt. And this part is simply ln q. Now we have a really neat formula for the entropy. Entropy is nr times t times d ln q over dt plus ln q. And this entropy is the Boltzmann entropy. The molar entropy is thus this. You know, you just divide both sides by the number of moles. You get this. This derivation assumes all particles are distinguishable. And what does that mean? That means if you look at, for example, 10 distinguishable particles, and then I ask you to turn around, and then I swap the positions and momenta of two particles. And then you turn back, look at those particles, and you know that I have swapped two particles. That means these particles are distinguishable. However, in thermodynamics, molecules, atoms are indistinguishable, and therefore the number of microstates should be divided by n factorial, because each combination of arrangement of particles, for each combination, there are n factorial identical permutations. I'm going to give you a numerical example. Let's say I have only 3 particles, A, B, and C. I'm labeling them A, B, and C, and make sure that we can tell which is which. And then let's say A, B, C occupy 3 different energy levels, level 1, level 2, and level 3. And then we have 3 factorial possible arrangements shown in this table. You know, A, B, and C can be in level 1, level 2, or level 3, and then we have 3 factorial arrangements. What if you have 4 particles occupying 4 different energy levels, and then you have 4 factorial different arrangements? We call them 4 factorial permutations. But if now I tell you these 4 molecules are identical, or this A, B, C are just identical, they are indistinguishable, I'm going to just call them A, and A. And right now, if you have 3 molecules, A, and A, occupy 3 different energy levels, there's only one possible arrangement. You'll say, well, a molecule A occupy energy level 1, a molecule A occupy energy level 2, and a molecule A occupy the energy level 3. That's it. There's only one possible arrangement when the particles are indistinguishable. So this is a very important concept in probability theory, between distinguishable particles and indistinguishable particles. It's also very important in thermodynamics. So now, if the particles are indistinguishable, again, if I give you 1 mole helium atoms, that's a lot, and I ask you to look at this 1 mole helium atoms, and then I ask you to turn around, and then I arbitrarily swap 2 atoms, and then I ask you to examine this same 1 mole helium atoms. You cannot tell if I swapped any 2 atoms or not. So again, those helium atoms are indistinguishable, unless you have 1 mole helium atoms, and some of those are helium-3, the others are helium-4, and then somehow we can distinguish helium-3 from helium-4. So that's a different scenario, though. Okay, so now we're gonna have to remove a lot identical microstates. So basically, we just need to divide the total number of microstates by n factorial, and that results in this. The entropy of the indistinguishable particles should be reduced by k sub b times the logarithm of n factorial. So again, this is because the microstates of this indistinguishable particles is equal to the number of microstates of distinguishable particles divided by n factorial. So that's why. All right, so we have this equation here for this kb times the logarithm of n factorial. This is just Stirling's approximation, and then we get this formula here. Now this part is for distinguishable particles, and this correction is for indistinguishable particles. And then this Q is a product of the translational partition function, rotational partition function, vibrational partition function, and electronic partition function. So I just replace the Q with this product. And then I'm going to separate the translational entropy from rotational entropy, from vibrational entropy, from electronic entropy. Oh, by the way, from here to here, I also divided both sides by the number of moles. So we're looking at the molar entropy here. And now I'm going to show you the molar translational entropy. So this part is the molar translational entropy. Look at the correction here. You have 1 minus ln n. I put it in this translational entropy term because for all chemicals, for all gases, they all have the translational motion. They do not necessarily have rotational motion or vibrational motion because they can be atoms. Atoms do not rotate. They do not vibrate. Therefore, we need to actually include this correction in the translational molar translational entropy just to make sense physically. So this is our molar translational entropy, and this is our molar rotational entropy, and this is our molar vibrational entropy, and this is our molar electronic entropy. So again, 1, 2, 3, 4. They correspond to the translational motion of the atoms or molecules, the rotational motion of the molecules, the vibrational motion of the molecules, and finally the motions of the electrons in the atoms or molecules. Now let's review the expressions of those partition functions. This is the translational partition function. It's proportional to temperature to the power 1.5. It's also proportional to volume. This is very important for the translational entropy. This is the rotational partition function for linear molecules. This is the rotational partition function for nonlinear molecules. And over here, this is the vibrational partition function for linear molecules, and this is for nonlinear molecules. Again, the difference between these two is, just pay attention here, this is 3n minus 5, 3n minus 6. Again, linear molecules have 3n minus 5 vibrational modes. Nonlinear molecules have 3n minus 6 vibrational modes. Now look at this. I'm just assuming the electronic partition function is 1. Okay, there are two assumptions here. First, the energy spacings between different electronic states is so large that the molecules or atoms all occupy the ground electronic state. That's one. Two, we neglect the spin multiplicity. For example, we're assuming the triplet electronic state of oxygen molecules are used as the reference. So we're just assuming this is just our reference. All right? And we're assuming the entropy of the perfect oxygen crystal at 0K is just 0. Okay, it's not R times Ln3, it's just 0. For an ideal monatomic gas, we do not have rotational or vibrational motions. So we say the partition functions of their rotations, non-existing rotations or non-existing vibrations is just simply 1. We just neglect the rotational entropy and vibrational entropy for atoms. They do not exist. So the monatomic gas possesses only translational entropy. So over here. What about electronic entropy? If you look at this, Q electronic is 1. You can just plug it in here. Ln1 is 0, Ln1 is 0. So electronic entropy is simply 0. All right? Electronic entropy is simply 0. Because if you plug in 1 here and 1 here, it's just 0. All right. Let's get back to the translational molar entropy. We plug in the expression of the translational partition function here and here. And then we just evaluate this too. This one is actually pretty easy because this part is simply a constant plus 3/2 Ln T. That constant does not depend on temperature. Okay, volume may change, but volume does not depend on temperature. Assuming we're looking at just a isochoric process, the volume is a constant. It does not depend on temperature. So that's why we just assume LNV, dLNV over dt is 0. And then we have only like 3/2 times Ln(t). Its first derivative is 3/2 divided by t. And then multiplied by t is just 3/2. All right? It's just, so the first term is just 3/2. Now let's look at the second term. So I just copied the second term here, and then you have plus 1 minus the logarithm of the number of particles. 3/2 plus 1 is 5/2. You get that here. And Lnv minus Ln is Lnv over n. I put it here. And finally, we have 1.5 times 2 pi mkbt over h to the power of 2. All right, so I combine this one and this one. All right, and then there's a coefficient in front. The reason I put this v and n together, v over n, is because v is an extensive property. And this n is also an extensive property. So v over n becomes an intensive property. And that's good because molar entropy is supposed to be an intensive property. It should not depend on the size of the system. And now if you look at this logarithm of v over n, this part does not depend on the size of the system. And over here, this one does not depend on the size of the system. So that's a good thing. And then if we multiply both sides by the number of moles, we get the translational entropy. The translational entropy is just NR times the sum of 3 terms, 5/2 LMV over the number of particles, plus 1.5 times the logarithm of 2 pi m kBt over h squared. Now let's get back to thermodynamics. In thermodynamics, we learned how to calculate the entropy change of a system in an isothermal expansion process. It's just NR times the logarithm of the ratio of volume. So now we can just use this equation. If you look at this equation, the translational entropy does depend on volume. It's right here. Okay, so if the temperature is constant, this part doesn't change. This part doesn't change. The number of particles doesn't change. And then we just focus on the difference in volume. And therefore, from this equation, from the translational entropy equation, we learned the entropy change in an isothermal expansion process is NR times the logarithm of V final over V initial. So this is thermodynamics. We just got this equation from the molar, from the translational entropy derived in statistical thermodynamics. If we are looking at a isochoric process and allow the temperature to change, and then in that case, this part doesn't change, this part doesn't change, we just need to look at this part. And specifically, we just need to look at LNT, because 2 pi m kb over h squared doesn't change. So really, we're just looking at 1.5 nr times 1.5 times the logarithm of T final over T initial. And if you still remember the equation for the entropy change in an isochoric process, it's just this. It's 1.5 times nr times the logarithm of T final over T initial for monatomic ideal gases. Again, monatomic ideal gases, so that we can neglect the rotations and the vibrations. And 1.5R is the CVM of those monatomic ideal gases. And 1.5 nR is CV of those monatomic ideal gases. We can predict the standard molar entropy of ideal monatomic gases at 290 K by doing some calculations, and we can actually calculate the entropy at any other temperature and under any other pressure. So again, we just need to use this equation for molar entropy. We can make this a little bit more convenient for our calculations. This V is equal to nRT over P. So I need to put nRT over P here. And this n is lowercase n, the number of moles. The number of moles over the number of particles is 1 over the Avogadro constant. So that's why this V over uppercase N is equal to RT over P over the Avogadro constant. So that's why this term can be rewritten in this form. Now let's look at this part. So this part is a bit difficult to calculate numerically because somehow you need to know the mass of one individual atom or the mass of one individual molecule. So my trick is I multiply this m by the Avogadro constant so that I can put molar mass on top. But of course, you need an Avogadro constant on the bottom. And this case of B, the Boltzmann constant is really small, so I'm going to multiply case of B by Avogadro constant, the Avogadro constant as well, to convert this case of B to R. And that's why you have the molar mass on top, the ideal gas constant on top, and I need to include this Avogadro constant to the power of 2 on the bottom. So again, this part is the mass of a particle times the Avogadro constant. The gas constant is case of B, the Boltzmann constant, multiplied by the Avogadro constant. So that's why. And then because this R, P, and N sub A are often constant, when we are looking at the molar entropy of a gas in the standard state. Standard state means 1 bar. So I'm going to just, put this 3 terms together. I'm going to just separate the L and T out. Okay, now look at this. You have 5 halves L and T. That's strange, right? But really, you have 1 L and T from here, and then you have 1.5 L and T from here. So together, 1 plus 1.5, you get 2.5 L and T here. And over here, you have just 1.5 times the logarithm of 2 pi molar mass ideal constant divided by the Avogadro constant squared, h squared. So again, this uppercase M is the molar mass. I want to emphasize this. When you do numerical calculations, be sure to use the SI unit. So I really want to remind you the molar mass of the hydrogen atom is 0.001 kilogram per mole if you are using this equation. The theoretical molar entropy of helium is calculated here. I just plugged in all those numbers. This is R, this is R, this is 1 bar, this is Avogadro constant. Over here, this is the temperature, and over here, this is pi. This is the molar mass of the helium atom in kilogram per mole. This is R, this is Avogadro constant squared. This is the Planck constant squared. Again, because these two are both squared. So I just did the multiplication first and then square the product. All right. The result is 126.1 joule per mole per Kelvin. If you look up the literature value of helium, I think it's 126.1 joule per mole per Kelvin. If you have molecules, and then we need to include the rotational entropy and the vibrational entropy. Again, you can assume the electronic entropy is 0 based on 2 assumptions. Assumption 1, the energy spaces between different electronic states are so large that we can neglect those excited states. So that's 1. 2, I'm going to just assume, even if you have a triplet ground electronic state, I'm going to set that to be 0 reference. I'm going to say the oxygen molecule with a triplet electronic ground state has a 0 entropy. Anyway, at 0K. So now we're going to just look at the rotational entropy and vibrational entropy. We'll just use these 2 equations. We need the rotational partition function. We need the vibrational partition function. So let's again take a molecule. For example, let's use HCl35. The reason I specify the mass number here is because if you have HCl37, it has a slightly larger translational entropy and also slightly larger rotational entropy. So now let's look at HCl35. We will calculate its molar entropy. It's going to be this number. So first, translational entropy. I don't like to actually calculate the molar entropy of HCl using this formula because it's really tedious. It's really tedious. Even if you have a calculator or if you have access to wolframalpha.com, I still do not like to type up all this on that website. So what I do is here I compare the translational entropy of HCl with the translational entropy of helium. All right, so what's the difference? Look, this is the same. This is the same for the 2 gases. This is the same for the 2 gases at the same temperature. And then if you look at this term, okay, the only thing that's different is the molar mass. So look, the difference between the translational entropy of HCl and the translational entropy of helium lies in this term, just the molar mass, 1.5 R times the logarithm of molar mass. All right, so that's what I did here. It's just be 1.5 R times the logarithm of the molar mass of HCl minus 1.5 times the logarithm of molar mass of helium. On top, this is the molar mass of HCl35. This is the molar mass of helium-4. Of course, there's helium-3, but let's not worry about that. Let's not worry about HCl37. And then we look at the difference between the molar entropy of HCl and the molar entropy of helium for their translational motions. The difference is 27.4. And we do know this is the molar translational entropy for helium, and therefore this plus the difference, we get 153.5 joule per mole per Kelvin. That's the molar translational entropy for HCl. I think I should put trans here just to make it clear that this I'm talking about just the translational entropy of HCl. We will calculate the rotational entropy and the vibrational entropy a bit later. But I need to make the correction here just to emphasize this is just the translational molar entropy of HCl. Now, molar rotational entropy of HCl. So again, we use this equation and we plug in the partition function for the rotation of HCl. It's just kBt over hCb. The symmetry number is 1. And then if you plug in this Q here, kBt over hCb here, you'll see this is going to be 1 over t. 1 over t times t is just 1. That's why the first term is equal to 1. I'll let you verify this. The second term is the logarithm of the rotational partition function. And hCb is equal to h bar squared over 2I. So why is that? Well, this is how B, the rotational constant, is defined. We defined B this way to ensure hCb is equal to h bar squared over 2I. This is just by definition. And then we can flip this 2I up, and h bar is h over 2 pi. So we get this formula. But again, this mu and in this case a b are both really small. So I multiply mu by the Avogadro constant. I multiply kb by the Avogadro constant. I get this formula, which is a bit more convenient for us to do numerical calculations. M1 and M2 are the molar mass in kilogram per mole of the two atoms in HCl. And REQ, that's the equilibrium bond distance. We know this equilibrium bond distance is 1.2746 angstroms. I got this number from the NIST website, and we can calculate the rotational entropy by plugging all the numbers. And remember, this is going to be 0.001 kilogram per mole, and M2 is, I think, 0.036 roughly kilogram per mole, and your number should be, in the end, 33 joule per mole per Kelvin. All right, so these two are the molar masses for hydrogen and Cl37. Chlorine 35. Now let's look at the molar vibrational entropy of HCl. This is actually negligible. You're going to see it's very close to 0. But anyway, let's derive this. So this is the derivation. This is the vibrational partition function. This is the vibrational partition function. Again, we are using a zero reference. We assume the lowest possible vibrational energy is 0 here and here. All right, we do not take that constant 0 point vibration energy into account. So if we take that into account, this one should be replaced by e to the power of negative half h nu over kBt. But again, the third law of thermodynamics is based on an assumption that the zero reference is the 0K internal energy, which includes the 0 point vibration energy and the electronic energy at 0K. All right, so we just need to do some mathematical operations here and here. We have a negative sign here because I need to kind of just flip this and flip this. So these two are flipped just for convenience. And then over here, we just need to take the first derivative of this guy. If we use the chain rule in calculus, we're going to see 1 over this guy right here. And then we need to take the first derivative of this guy. It's going to be over here. And now we can further simplify this term. I mean, we can just multiply the numerator and denominator by e to the power of positive h nu over kBt, and I think you'll get this. And also, there's a negative sign here, there's a negative sign here, so they cancel. It becomes a positive term here. However, you have a negative sign here, a plus sign here, so you put a negative sign here. But this is always positive, so this part is always positive because this part is always less than 1, and this part is always positive as well. Now let's calculate the vibrational molar entropy for HCl. We need to know the vibrational frequency or vibrational wave number of HCl. The wave number is 2900 wave numbers. You need to convert this to the SI unit. So it's actually 290,000 per meter. So if you have trouble doing unit conversion, just tell yourself that you can put 2,900 waves within 1 centimeters. Then, of course, you can put more waves in 1 meters. You can put 290,000 waves in 1 meters, right? So this number should be 100 times larger than this number, all right? And then we can actually compute h nu over kb first, all right? Because if we do this, we can actually calculate h nu over kBt for any other temperatures, other than the room temperature. So h nu over kb is roughly 4,200. So at the room temperature, h nu over kBt is 14. So nice. I can plug in 14 here, and 14 here. All right. So this is the molar entropy. The molar vibrational entropy of HCl. But look at this number. E to the power of 14 is such a huge number that this term can be neglected. And e to the power of negative 14 is such a small number. It's much smaller than 1. So I'm going to say this is also 0. This is negligible. This is negligible. Therefore, the molar vibrational entropy is 0 at the room temperature. Now let's look at this equation again. What about 600 Kelvin? That's a very high temperature. At 600 Kelvin, h nu over kBt is 7. Now you have 7 over e to the power of 7 minus 1 minus the logarithm of 1 minus e to the power of negative 7. So again, 7 is much, much smaller than e to the power of 7 minus 1. So this is negligible. And also 1 minus e to the power of negative 7 is also very, very close to 1. I think it could be 0.999, something like that. So this is still 0. This is still 0, even at 600 K. You can assume the molar vibrational energy of HCl is, again, 0. So when do we observe molar vibrational entropy? When you have vibrational modes with very small wave numbers. So when you have very small wave numbers, so if this is very small, and you have a small number. So if h nu is close to kBt, the ratio is 1. And then you cannot neglect these two terms. It's going to be just 1 over e minus 1. I think that's roughly 0.4. No. It's roughly 0.6 here. And then 1 minus e to the power of negative 1. Again, this is non-zero. So in that situation, if h nu is close to kBt, you need to calculate the molar vibrational entropy. And it's not 0. It's significant. It's significant. The molar vibrational entropy is significant for the vibrational modes with small wave numbers. We can almost always assume the molar electronic entropy to be 0. Okay, and for HCl, we make that assumption as well. Therefore, the molar entropy of HCl35 is the translational molar entropy plus the rotational molar entropy plus the vibrational molar entropy plus the electronic molar entropy. The result is 186.5. The literature value is 186.9. Okay, it's pretty good. Similarly, we can hand calculate the molar entropy of any other ideal gases or even real gases. We can estimate the molar entropy of any real gases using the ideal gas approximation, though, at any temperature and any pressure using this equation. This part is the translational molar entropy. This part is the rotational molar entropy. This part is the vibrational entropy. Again, I assume the electronic partition function is a constant 1. So now this is the formula for translational partition function. You just need to plug this in here and in here. And over here, this is the rotational partition function for linear molecules and for nonlinear molecules. This is the vibrational partition function for linear molecules and here for nonlinear molecules. So again, we assumed the electronic partition function is 1 for all gases.